Here we go. My favorite student, good old Anne. In a flat corner with a 30-meter radius, a car barely negotiates a turn. Why did I say barely? What we're really saying is, what's the minimum, sorry, in this case, maximum speed it can do it at? Could be going slower. What was the key here? I said the key here was to draw the correct free body diagram. What I drew was a front view. I said you wanted to imagine the car coming out of the page towards you, going around the center of the circle like that. That made it a way easier free body diagram. No, Alex, you don't have to draw the car. You could just put a dot there. But this is just to help you visualize what I'm talking about. We said, what are the forces acting on it? We had gravity down, normal force up. There has to be a force pointing towards the center. In this case, we decided it had to be friction, which explains why you can't corner very well on ice. So my equation is going to look like this. Friction is what's pushing me in a circle. Which version of A am I going to use? Well, since it asked for the speed, I better use the one with speed in it. So my next line would be mv squared over r. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. Can small cars and big trucks go on the same roads? Why? Well, that's a bonus. So, if you'll notice on this line, Sarah, there's mu, g, v, and r, 4 variables. As far as I'm concerned, I can give you any 3, find the 4th. Even putting you on a mystery planet and saying, find the acceleration due to gravity on the mystery planet. I could ask you to get the g by itself. Here they want the v by itself. Oh, it's going to be our old friend, the square root of g, although it's going to be, I think, v equals the square root of mu g. The square root of, what's mu? I don't know what's mu with you. 0.655, good sticky tires. 9.8 times 30. V equals 0.655 times 9.8 times 30. Square root. 13.9, is that right? So if you got that, 3 out of 3. 1, 2, 3, 4, 5. Otherwise, I'd probably give you a half mark if I saw that. Half mark if I saw that. Half mark for getting the v by itself. Half mark for the numbers. And then 1 mark for the answer. Probably something like that. If you took the corner at this speed, 13.9 meters per second, you would feel through the steering wheel, especially if you're an experienced driver, you could just feel that you were about to lose traction. So, of course, you would never take it at that speed. You would do it much slower. A 2.5 gram spider, first thing I did was go, nice try, Mr. Dewick. 0.0025 kilograms, because kilograms is divided by 1,000 to go from grams to kilograms. So on a platform rotating with a period of, okay, find the speed of the spider. Oh, nice try again, Mr. Dewick. 0.19 meters. I think we have kind of the same free body diagram, but instead of a car, we just got a little spider sitting there. But what are the forces acting on it? Get the obvious one. Gravity. Also a normal force. And what's pulling it around in a circle? I think friction again. Now, part A said find the speed. I got 2 into this. I was doing the free body diagram already. I think to find the speed, I can just go 2 pi r over the period. That's right from my formula sheet. It's circular speed. So I can go 2 times pi times r, 0.19 divided by 0.682. Did you get a speed of 1.75 and change? meters per second. B is where I'm going to use my free body diagram. They want me to find the friction coefficient. They want me to find mu. So again, I think I would say friction is what's pulling me in a circle. I could use either v squared over r or 4 pi squared r over t squared. I could use my answer from A. You know what? I'm a good test writer, so I'm going to use the 4 pi squared r over t squared, because that's data that they gave me just in case I made a typo in part A. And mu times the I don't know the normal force. Oh, but look. Okay. Did I need to give you the mass of the spider? Technically, no. So a big tarantula could also make it around this corner as well, assuming it had the same level of stickiness on its feet. Lena, how will I get the mu by itself? How will I move the g over? Yeah. How would I get the r by itself? How would I move the 4 pi squared over? How would I move the t squared over? Times. How would I get the t by itself? I think because it's on the bottom, first thing I would do is times it to the top on this side. Then I would divide the mu g over. That would give me a t squared, square root. So again, as far as I'm concerned, 1, 2, 3, 4 variables. If I give you any 3, you can find the 4th. That's my point. Here, that works. Let's see, Mr. Dewick. Mu is going to be 4 pi squared 0.19 divided by 9.8. What was t? 0.682. Don't forget the squared. Most common silly mistake is forgetting this last squared, because your brain has written so many squareds, you've kind of mentally, I've done it all. You haven't. 4 pi squared times 0.19 divided by bracket 9.8 times 0.682 squared. 1.65, which made me nervous, but then I looked at the note. It said a spider has sticky feet, so mu can be bigger than 1. It's having to use its stickiness to stay in place. It's not just using straight friction. It's doing it. I don't know how spiders, if they secrete a glue or if there's a molecular thing going on. I need to look that up, but something's going on. Units. Oh, there are none. So for 3 marks, 1, 2, 3, 4, I'd probably go something like this. 1 mark for that, half mark for that, half mark for that, 1 mark for the answer. And for 2 marks up here, I'd probably go 1 mark for that, half mark for the numbers, half mark for the answer. I don't know, something like that. Then I would turn the page. The gravitron. Oh. Person is riding the gravitron. The coefficient of friction between the rider and the wall is that. What's the minimum safe radius? So what we need to recognize, if we do just a little side view of the wall of the gravitron, so here's the person, what are the forces acting on them? Get the obvious one. Which way? Down. Are they sliding down or up? No. So I know there has to be a counteracting force up. And also, if they're tracing out a circle, I know there has to be a force pushing inwards. What's pushing them around in a circle? Which force is that? Okay, we know it's the normal force. What's the vertical force then? Friction. So you actually are going to end up with 2 equations. One of your equations, which we'll use a bit later, is realizing that mg is equal to friction. But I would start out by saying, okay, normal force is what's pulling me in a circle, or pushing me in a circle. Which version of the normal force am I going to use? They gave me the period, so I'm going to use the 4, the pi squared r over t squared. Which version of the circular force? Did I say normal force? I think circular force is what I'm going to use. Problem is the normal force. I don't know the normal force. Now I walk over here. Keegan, friction is what times what? Did you say normal force? So I can go like this. mg equals mu Fn. In fact, I can replace the normal force not with mu mg, which would be flat level friction, but with, I guess, mg over mu. So here I can go mg over mu. Can little kids and grown-ups go on this ride? Why? Well, that's a bonus. And again here, I've got g, mu, r, t. There's 4 variables. As far as I'm concerned, I've got a bunch of different versions of this test. If I give you any 3 of the variables, you can find the 4th. I would have spun several different versions of the gravitron question. Here they want r by itself. I guess the t squared is going to get multiplied. The 4 pi squared is going to get divided. The r is going to drop down. There's going to be a g. The t squared is going to get multiplied. The mu stays where it is, and the 4 pi squared gets divided. Now it's going to be just plugging in the numbers. R is going to be 9.8, 3.2, don't forget the squared, divided by, what's mu? 0.45 times 4 pi squared. Don't need quite that big long a fraction bar. No idea. 9.8 times 3.2 squared divided by bracket 0.45 times 4 pi squared, close bracket. Do you get 5.65? I guess meters? If you got that, and you showed work, I would give you 7 out of 7. Otherwise, 1, 2, 3, 4, 5, 6. Bonus, I wrote 7 lines, so I'd probably go 1 mark if I saw that, 1 mark for 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 that. Probably something like that. That wasn't too bad. Kind of fun. I got to imagine being on the gravitron. And we've talked a little bit, I showed you the video of the rotating room and how strange objects seem to move in that fake gravity, especially if you throw something, it will appear to you to be curving, even though relative to the Earth it's still going in a straight line at steady speed. Okay, let me hit pause.